So the next topic is going to follow the molecular geometry. Once you have molecular geometry decided, that determines where the bonds are pointing. Now we're going to look at the polarity of individual bonds and see how they combine to form an overall polarity of the molecule. Okay, so for example, let's look at carbon dioxide. Now we already know the oxygen is more electronegative, so this bond is polar toward the oxygen end. However, on this end is another oxygen pulling exactly with the same amount of electronegativity toward the other end. So this is like a tug of war where basically you have no net dipole moment. These things add together head to tail. So if you're experienced with adding vectors, all you have to know is that two things pointing exactly opposite are going to cancel when you add them together. Okay, so for example, it's like going somewhere and going back. You know, you have a vector that says you're going to the right, and then if you come back to the left, you're back where you started. You went nowhere. So that's what happens. This is nonpolar. All right, now let's look at BF3. This is trigonal planar, no lone pairs, but the bonds are very polar. There's a bond pointing that way at one of the corners of the triangle, one exactly the same strength because it's the same two atoms involved, and one pointing up. Okay, so it turns out that when you add all these three together, they exactly cancel. This is going to happen whenever the electronic geometry is one of the 5 basic shapes and the ends are all the same. So for example, both ends in linear are the same. You get 0 dipole moment, it's nonpolar. In trigonal planar, if you have all 3 bonds the same, it's going to be nonpolar. It doesn't matter if the bond is polar, the molecule polarity, which is the sum of all these individual bond dipoles, might give 0. All right, now this one here is somewhat different. Okay, this is trigonal planar still, but the CO bond is polar toward the oxygen. The CH bond is polar. It's not pulling out like the CO bond is, it's pulling in. And this one's pulling in too. Maybe not nearly so much. But these do not all add and cancel because all of these arrows are pointing to the right. It says, you know, electron density is going to the right, although with the video it might be on your left. All right, so polar. Because the individual bond dipoles add together, they don't cancel. All right, now what about this one here, the sulfur dioxide? Well, the bond is polar toward the oxygens, and they both point down, and so the net resulting dipole moment is what you get when you add these two together is straight down. Turns out that there's a component pulling out to this side. It's exactly canceled by the component pulling out to this side. If you do a little trigonometry, you can figure that out. All right, so don't cancel, do cancel, don't cancel, do cancel. Nonpolar, polar, nonpolar, polar. All right, what about tetrahedral? Well, this is an example of one of your basic electronic geometries, which is if the molecular geometry has all the same 4 corners in the tetrahedron, then it's going to be nonpolar. It doesn't matter what the polarity of the individual bonds is. They're all opposite of each other if they're all the same. So this could be the same as you get for carbon tetrachloride. If you put chlorines out here, the bonds will be polar in the other direction toward the chlorine, but they still all cancel. Ammonia. Now in ammonia, they don't cancel because this one's pointing down, this one's pointing down, this one's pointing down, although it's kind of hard to see, but they're all pointing down somewhat in this pyramid. Remember, this is a trigonal-based pyramid with the nitrogen on top and all the hydrogen bonded to it below, so that means all the polar bonds are pointing down somewhat. So the net result is electrons are being pulled straight down when you look at them in total. So this is polar. Then water is polar. It's a lot easier to see in water than it is ammonia. Whoops, wrong way, polar toward the oxygen. And I got my arrows backwards here, excuse me. all the arrows should be pointing at the nitrogen. So the electrons are all being pulled up rather than down. Okay, you can correct that yourself. Yeah, I'll correct it. Why not? Easy enough. Pointing toward the more electronegative element, more electronegative and more electronegative. All pointing up. There we go. All right, this one's pointing up. This one's pointing up. And the net result is electrons are being pulled up toward the oxygen, away from the hydrogens. This is polar. Okay, so to recap, what we've done is we've taken the Lewis structures, counted the groups of electrons to determine the way the electrons are arranged, which in turn determines how the atoms are arranged. And how the atoms are arranged in their bonds, how the bond dipoles are arranged, determine whether the overall molecule is polar or nonpolar. So the next video is going to talk about why that's important.